All right, so I've been introducing everybody else throughout today, but now I have the pleasure of introducing myself. I'm James, I'm from Threshold, and today I'm going to be talking to you about Taco. Taco is an access control layer that is end-to-end encrypted, end-to-end decentralized, and has been since its inception. Why is being decentralized from day one? Why is that a big deal? So the people who are building on top of Taco are dealing with some pretty sensitive stuff. Imagine having to secure something as important as inheritance or seed phrase recovery or health data. These aren't hypothetical situations. These are things that people are building right now with Taco, and they need private, secure, trust minimized solutions from day one. They are not problem spaces that can accept any sort of compromise when it comes to their decentralization. Before I get into too much detail, here's the link to a nice simple demo. If you'd like to, it just takes you to a GitHub page. It's a one-page Node.js demo. I'll put that back up in a few minutes as well. So first of all, what is Threshold? Threshold is the first successful on-chain merger between two existing projects. Those two projects were both well-established powerhouses, NuCypher and Keep, and the result of that merge was a multi-application network centered around the concept of threshold cryptography. So consider the traditional approach to handling sensitive cryptographic operations. For example, digital signing signatures, generating randomness, or managing decryption keys. These operations in the past would have been handled by one entity, one server. And that's very efficient, but it centralizes trust and power, and those are things we're really trying to avoid at the moment. Threshold Network addresses those issues by spreading the cryptographic operations across a large network of nodes. Independent nodes, independent entities, that's an important distinction. So within the Threshold Network, we have several applications that are built on top of threshold cryptography. The one notable one is TBTC, which is the largest decentralized Bitcoin bridge to Ethereum, currently with a TVL of, I think, over $180 million at the moment, and growing fast. And that same network is what's powering Taco, the access control product. It's doing the whole thing. So why does Web3 need Taco? Why is this important? So in our journey towards these better digital spaces, we're aiming for platforms that respect our privacy, they don't exploit us, everything is fair and transparent. And a often overlooked piece of that puzzle is selective decryption. What do I mean by that? It's making sure that only correct devices, correct individuals have access to certain data. It's crucial for our digital interactions, like who has access to what. And actually it's applicable outside of Web3 as well. Think of any time you are paying for something online and getting something in return, that is a access control that is happening with a very simple condition of have you paid. And at the moment, our tools are limited as developers. There are traditional methods like asymmetric encryption and public key infrastructure, and these are great. These are very secure. They do all the processing is client side, which is excellent, but they are difficult to scale well whilst maintaining user friendliness. Think like PGP on your email. It's not mainstream, despite being around for a very long time. Another alternative is to use centralized services, things like Amazon KMS. They're very convenient, but again, you're placing significant trust in a third party who has repeatedly proven they do not deserve our trust. And then the final, arguably worst option is what we refer to as DINOs. DINOs will eventually go extinct. It stands for decentralized in name only. There are plenty of services across the Web3 space that claim decentralization, and when you dig in, you'll find that the essential decryption keys effectively are held by either one entity or a small permissioned set of entities. Think Ren BTC, which hailed itself as a decentralized Bitcoin to Ethereum bridge and then wasn't. It was just completely drained. These are the kind of things we're talking about. So is Taco any different? Yes, it absolutely is. Let's get into that. So how does all of this work? How is Taco decentralized from day one? So imagine we need to secure some data. First, we begin by selecting a set of nodes from the threshold network. Let's say select 30 nodes from the threshold network. We're going to refer to this group as a cohort of nodes. The cohort of nodes undertake a distributed key generation process, DKG. This is a really important step. During this process, they are generating and sharing and aggregating and verifying a bunch of cryptographic material. And if any node attempts to compromise the process, the whole thing fails. So the entire operation is designed such that only honest participation by all nodes will lead to success. If anyone starts messing around, boom, it fails. Start again with a different set of nodes. The end result of the DKG process is a public key and a distributed private key. The public key is stored on chain for applications to use, and each node in the cohort keeps its own piece of that distributed private key. As a data owner, what do I then do as a data owner? I want to encrypt and share stuff. So first you would define the specific conditions under which your data can be encrypted. For example, you're running a live stream and it can only be accessed if a viewer can prove that they own 2 specific NFTs. Just a random example. Those conditions that we've just outlined, they are embedded within the data at encryption time. So they're all packaged up together. They're super flexible. I'll get into them a bit more in a minute. But they are very modular and composable, and you can have quite complex condition logic if you require. That encrypted payload can then be stored anywhere. This is super important. So Taco is completely storage agnostic, which opens up a whole world. It allows us to use our favorite decentralized storage solutions, things like Arweave, things like IPFS, that have no encryption or sharing built in. Suddenly they're completely opened up. I can even use old school third-party centralized services, Amazon, Google, all of these kind of things, any cloud provider you can think of, and I am safe in the knowledge that the only people who can access my data are those who satisfy the conditions I set. No one else will be able to. But what about on the consumer side? If I satisfy the conditions, I want to be sure that I have access to the data. That's it has to work both ways. So as a recipient, I go and retrieve this encrypted payload, whether it's on Arweave, maybe someone emailed it to me in a side channel. However I get it, I then present it along with my credentials to the threshold network. And this is where the threshold cryptography magic happens. When I present this package and I present my credentials to the network, each node goes and verifies those credentials. It checks those credentials against the conditions, and each node makes a decision on, are the predefined conditions met, and decides whether to grant access and return a decryption fragment. So again, this is a really important piece. The nodes are just returning decryption fragments. They are not decrypting the data. If a recipient is then able to collect enough decryption fragments and reach the threshold, which is the threshold in threshold cryptography, let's say 20 of 30, once they've collected those 20 fragments, they will be able to rebuild the underlying plaintext locally. So the nodes never have any access to the, they don't see the encrypted data, they don't see the plaintext, they see nothing. They're just sending back these little pieces that mean the end recipient can plug them all together and rebuild the things they need to build. So let's have a look at case studies. This is one of our earliest adopters, Masterfile. Masterfile are attempting to transform how we think about digital content. So imagine owning a movie or some music, piece of art, etc., not just as a digital file, but an asset with associated decryption rights. People have talked about doing this with NFTs, and it's never quite worked. This is how you get it to work. By combining, they're building on Taco and Arweave. So when you buy an NFT from Masterfile, it's not just a receipt that you bought this film or this art. It also acts as the decryption rights. Ownership of that NFT is what grants you access to the content. And so you have, because they're using Arweave, which is permanent storage, and they're using Taco, which will give you permanent access as long as you satisfy the conditions, you now have access to this content forever. It is effectively yours until you decide to sell the NFT or transfer it to someone else or whatever. You have full ownership of those access rights. And at the same time, the creator is safe and happy knowing that they are getting paid directly by the sale of these NFTs, and they have no fear of unauthorized distribution. The only people who can access own the NFTs. So it goes both ways, both parties win. If we compare this to the traditional model, say like Spotify, you spend years building up your nice playlists on Spotify, and then 1 month you don't pay your subscription, and boom, it's gone. It's not yours. You're locked into paying quite a large sum of money over the course of your lifetime. When you think of, I'm not going to stop listening to music as I get older. I'm going to be paying my Spotify subscription until the day I die, which is a lot of money over the course of a lifetime of a person. These traditional media companies are actually really interested in Web3 and using it for securing their media, but they are wary of platforms, using platforms like OpenSea, where there's a real centralization risk. They're the ones that are actually pushing for they're the ones that are pushing for true decentralization because they're scared of unauthorized distribution and digital rights management, and all that kind of stuff. And this is what Taco solves. All right, should we have a look at some code? Live demo time. What could possibly go wrong? Let's see. Sorry, I'm mirroring my screen. Oh, great. Perfect. Oh, no, not perfect. Aha, knew it. All right. So I'm just going to quickly pop into this .env file. This is not how you should do it in production. This is just some basic configuration. We need an RPC provider. We need an encryptor provider private key, and we need a consumer private key. The ritual ID refers to the cohort of nodes that we talked about before that did the DKG ceremony, and the domain is to peer, which is what we are calling our testnet. We will then do some basic setup. I'm just reading in. We need a connection. We need to read in those private keys. We're going to go and get the ritual, connect to the provider using ethers, and log some stuff. This is just some setup. All right, so let's encrypt. First thing we do is, we can see here, line 49, message equals 2 bytes of the message string. So we're just going to convert the message, plain text to bytes. Then we're going to set up a condition. So our condition is these few lines. The chain is 80002, which is Polygon's testnet. The method is getBalance. We want to check the user address, and we're going to compare greater than 0. So all this is doing is checking that the user has a positive balance. As I said, these conditions can be extremely generic. We can provide a contract address in the condition, and then any method that we like that exists on that contract, and any return value test. So if you have extremely complex condition logic, you can just deploy a smart contract that contains it all, meaning it's super transparent for your adopters and users, and then point this at it. They're also composable. You can do things like checking the block height if you want time-based conditions. So the block height has to be greater than this and less than this, so you get a nice specific window. And at the same time, this function on this contract returns true, and this function on this other contract returns false. And the user must have a positive balance. You can just plug all of these things into each other and get some nice, complicated and updatable condition logic. And then we call the encrypt function from the Tacker Web API. This is literally as complicated as it gets. Provide the provider, the domain, which was the testnet, the message, our condition, which cohort we're using, and who is signing this, who is actually encrypting this. And then we'll return those bytes. On the decrypting side, it's even easier. We get a message kit using from bytes, and then we call the decrypt method again from the Tacker Web API and provide a few of those same pieces of information, and that's all we need to return. It looks like more lines of code than it is, but really there are about 3 lines of code that are actually happening here. We've abstracted away all of the work for you. And then, so if I run this example, this is actually what will be happening. I'm just going to connect, print the string, what the ciphertext is, get the decrypted bytes. I will, call encrypt 2 bytes, print what I get. Then I'm going to call decrypt from bytes and print what I get. And of course, they should be equal if everything is working well. So let's, of course, my terminal is opened on the other window. Apologies. Maybe I can do it this time. There we go, we have a terminal. Excellent. Just gonna all right. Let's run this. So we're printing our config. All right, it's already done. Amazing. It's super fast. This is our message. This is the ciphertext when we encrypt it. We send it off to the Taco, the threshold network, and it all comes back and we're able to decrypt locally. Amazing. That's because I know that that private key has a positive balance. How do I prove that this is real and I'm not just, printing some nice stuff for you? Well, let's change the condition. Let's make the condition such that I have an absolutely massive balance on testnet. Something like this. I can tell you that I don't have this much testnet polygonmatic. So now, encrypting again. Excellent. We get the ciphertext back. We then take that ciphertext, send it to the threshold network, and this time, the nodes say absolutely not. So the threshold of responses is not met. That's the threshold in threshold cryptography. And we can see the individual responses. Decryption conditions not satisfied. The nodes all agree that the decryption conditions are not satisfied. Okay, so yeah, that's as easy as it is. Just a few lines of code and you've got your decentralized end-to-end access control. We have a booth downstairs, and very active Discord, bounties. Please come and say hello. If you have any questions, come downstairs and say hello. We're nice and friendly. And thank you for listening. I really appreciate it.